In GCSE we learned that atoms comprise of a nucleus of protons and neutrons surrounded by shells of electrons. This is known as the Ernest-Rutherford model. Protons have a relative mass of +1 and a relative charge of +1. Neutrons have a +1 mass but no charge, and electrons have a negligible mass but have a relative charge of -1. However, this is not the case at AS level, as there are many more particles that we have to know. Subatomic particles are divided into two main categories, leptons and hadrons. Hadrons are then divided into two other categories, baryons and mesons. Leptons are things such as muons, electrons and neutrinos. Baryons are things such as protons and neutrons, and mesons are things such as pions and kaons. Mesons are made of one quark and one antiquark. Baryons are made of 3 quarks or 3 antiquarks, and leptons are fundamental, meaning they are not made of quarks. However, there are also antimatter versions of all these particles. For instance, there are antimuons, antineutrinos, and antielectrons, otherwise known as positrons. As mentioned earlier, some subatomic particles are made of quarks, and just to make things even more confusing, there are 6 types, or flavours, that you need to know at AS level. Down, up, strange, anti-down, anti-up, and anti-strange. The table on screen shows the properties of these quarks: charge, baryon number, and strangeness. An American physicist called Richard Feynman came up with a way of visualising forces in exchange particles. The line in Feynman's diagrams represent entering and leaving, not direction. Number 3 represents beta minus decay, for example. In order for these interactions to take place, 4 things must be preserved: the charge, the baryon number, the lepton number, and the strangeness. If all of these things are preserved, the interaction is possible. The GCSE version of beta plus decay is impossible, as the lepton number is not preserved. A package of light is called a photon. The higher the frequency of the light, the more energy it has, as energy equals Planck's constant times frequency. If the frequency is high enough, it can split into a particle and an antiparticle, as mass is proportional to energy according to Einstein's E equals mc squared. This is known as pair production.